Okay, this is our last section. We're going to talk about congruence transformations. Okay, basically, this is something that you should have already learned prior to this year. If you watch Miss Wilson, thank you. If you watch Miss Wilson's video, she'll talk about learning in algebra, but we don't teach it in algebra anymore. So you probably learned it in 8th grade math, 7th grade, whatever grade it was. But basically, we're going to talk about moving geometric figures. Okay, specifically today, triangles. So this can also be incorporated into your project, your Christmas project. If you want to do that, that might help. But a transformation moves or changes the geometric figure. Today we're going to focus mainly on moving. When we change a geometric figure, the change of a geometric figure is more of a dilation. And a dilation is when you make the figure bigger or smaller. Okay, we're not doing any of that today. Then you're going to have a new format today, a new notation that you probably aren't familiar with, that probably was not taught in elementary or middle school. Middle school or last year. And what's going to happen is that your new figure is called an image, so they'll call it image. If you look at this right here, this A with the arrow to A1, okay, that A1 or whatever, little looks like an apostrophe, that's prime. I'm going to call it A prime, okay? Not to be confused with like a prime number, it's just telling you the new figure, okay? That's just saying that's the figure that is new from the transformation. A is the original figure, A prime is the new figure. And then of course when you do a translation, this is why our geometric figure is not changing. When you do a translation, you move every point exactly the same. And that's just some basic information. Most of this is pretty easy. Like I said, the only complicated part of this is maybe the rotations. Rotations seem to be somewhat tricky. And it's really just one type of rotation. Okay, hopefully, does everybody have this? Okay. So here, we're going to look at two triangles, triangle ABC, and then we have A prime, B prime, C prime. And we are going to do some transformations with it. Now notice, you see here that it's got this little horizontal arrow of A and a vertical arrow of B. Okay, that horizontal arrow is in the A value just represents the fact that any kind of shift horizontally is going to be notated by the A, okay, by lowercase a. That lowercase a has nothing to do with this A here from the triangle or the A prime from the triangle. The lowercase a is simply a designation for a horizontal movement. Just like that lowercase b there is a designation for a vertical movement. Okay, it has nothing to do with the B or the B prime. And then you'll see here on the bottom, this is our new notation. Okay, this x, y transforms to x plus a, comma, y plus a. So basically what this is saying is if I take the coordinates of my A form, that goes here, right? That's the original figure. And then, in order to transform it, I've either got to A, follow this transformation notation, or B, I've got to create the notation. So this is kind of a new concept, which you're probably not used to because we didn't do this when I did teach this in Algebra 1. We didn't do that on a regular basis. So basically what this is telling you is saying, hey, this is going to move however many units A to the right or left and how many units B to the left or right. So if I move to the left, what happens to my A value? Yeah, it becomes negative. If I move to the right, I'm sorry, if I move down, what happens to my b value? It also becomes negative. And somebody in the last class asked, do I have to put plus minus? No, you just put negative, like a minus a, or x minus a, y minus b. Okay? And again, that's our notation. You're going to get very familiar with this notation. You'll see more as we go along in the examples. Okay? Does anybody need this? Okay. All right. Go ahead and put your phones away while even if you're looking at Blackboard or whatever, put your phones away. During lecture time, it is super strict. All right. So let's say we have this example right here where you have two triangles. It's giving you a coordinate of one of the vertexes. Or one of the vertices. It's either -4 and 2, and then I can transform it to this over here. Now, notice when I transform it, how did I get this -4 to become a 2? Which way am I moving? You can look at the picture. I'm going to the right, so I'm going to have plus something, right? What am I adding to get 2? 6, all right? So I'm taking this -4 plus 6. Okay? How am I getting the y value to go to -2? Okay, I can look at the picture and see I'm going down, and I happen to subtract 4, so I'm going down 4 units. So if I write the transformation notation, or if I write this in the notation form that we have, I have my original value xy transforms to x plus 6, comma y minus 4. Why did I leave it in a generic form like this? Why didn't I just put 2 and -2? Well, it helps you tell what you did, but what else? Yes?
Does it work for the triangles?
Yeah, it works for the rest of the vertices, right? I can move the rest of them now, and that's the point. Remember, we're not just moving a point to point. This tells me how to move one point. But now, if I would tell you this, hey, that only tells me one point. Now, obviously, I don't have all the other points listed, but now I can use it for this one. That gave me how I got this. So now, algebraically, rather than counting necessarily, or looking at the coordinates, algebraically, I can figure out what the rest of these vertices are for the new one. Okay? So that's exactly why. It's good for the entire triangle, the entire transformation. Okay, let's look at reflection. This is a mirror image, just like reflection makes sense, right? It's logical. Reflections are I think to me, are easier than anything else. Did everybody have what they need on that last page?
What was it called?
The last thing we just did? Transformation.
Oh.
Yeah, that's the transformation. Or translation, excuse me. Now we're doing a reflection. Just like in a mirror, like I said, you're looking at a mirror, you're kind of seeing yourself, but you're seeing a little bit of different version, okay? If I want to reflect it across the y-axis, I'm basically going to be looking at myself, right? Reflections are easier because if I was actually to graph these, I would just count. 1, 2, 1, 2. Or 1, 2, 3, 4, 1, 2, 3, 4. I could just count the same distance or equidistance from the y-axis. But I also get something else out of this particular thing. Using my notation again, I take my original point, and what happens to my new coordinates?
Negative.
Okay, it becomes a negative x, but let's change our thought process a little bit. This is kind of how I taught my Algebra 1 students last year. Instead of always looking at a negative sign as a negative number, we can also consider it as what?
Subtract.
Not subtraction, opposite. It's also the opposite. Okay, it is subtraction, but in this case, it's the opposite. Because the thing about this is my original x value could be negative. I've got to be very conscious of the fact that negative just means the opposite. So if it starts as a negative, the opposite is a positive. If it starts as a positive, the opposite's a negative. What happens to my y value when I cross the y-axis? It stays the same. Nothing happens, right? Nothing happens. Okay? So when I cross the y-axis, the y values stay the same. So what do you think happens when I cross the x-axis? Yeah, the x values stay the same, and then what happens to my y value?
Negative.
It's not negative. It's the opposite, right? It's the opposite. And again, I'm just counting here. 1, 2, 1, 2. 1, 2, 1, 2. It's just the same distance from there. Now somebody asked me in another class, said, hey, well, what happens if can I do a fancy little trick like this one up here in the corner? Can I do a little fancy deal like that if I'm crossing just x equals 1? No, if you're just crossing any other vertical or horizontal line, then you just have to count. There's no fancy little trick like that. Is that your question? Okay. Now again, here's the other thing too. You need to kind of know this algebraically too, and don't just assume that you can count everything, because like on your test, you're going to be told, hey, you have these things, but you're not necessarily going to be given a diagram. So rather than trying to diagram everything, because unfortunately you have to finish in class, rather than being told you have to diagram everything, then you could go ahead and do it algebraically like you see there. Okay? All right, so let's talk about rotations. Rotations are slightly more complicated. We have two ways we can rotate. We can go clockwise or counterclockwise. Pretty self-explanatory. I'm going to briefly touch on counterclockwise, and then I'm going to show you something on clockwise in just a minute when we get to our diagrams. What happens when you go clockwise? What happens or counterclockwise? What happens from the original to the new point? They switch. It ends up being the inverse, right? Because that's what the switch is. So you take this x and y value, and when you go to the new point, you switch them, and then what happens to the y value? It's the opposite, right? So basically, if I have this 3,4, this point 3,4, I switch it over here, and then make the first one negative. Now, I still plot this like normal. This is an x, y value. This is an x, y value. This just tells me how I got there. Does that make sense? Yes? No? Pretty simple. And then, of course, with the 180-degree rotation, everything is what? Opposite, right? Because if I'm standing here, like I told the other class, if I'm standing here and I rotate 180 degrees, I'd be standing on my head. Okay, that'd be the opposite. Okay. On the bottom here, it says keep in mind what quadrant you're going. Keep in mind what quadrant you're going to for the signs. Basically, if you don't think of things in terms of opposite, you're looking at negative and positive. When you do a rotation or a translation or a transformation or whatever, okay, if you go from quadrant 1, which is all positive, to quadrant 3, that's all negative, make sure that your coordinates or your ordered pairs reflect that. All right, any questions? Let's look at some actual transformations, okay? We're going to quickly look at your translation. Translation is simple. Here, it's giving me x, y. I'm going to translate it 7 units. So which way am I going?
To the right.
To the right. And then I'm going to go which way on the y-axis? Down. So my triangle should go to the right and down. So let's take a look. Yeah, here it is. So if I count from my C point here, make these a little easier to count. I have 1, 2, 3, 4, 5, 6, 7. That's my positive 7. And then down 1, 2. Pretty simple. Okay, if I want to reflect across the x-axis, or sorry, the y-axis, what's going to stay the same? The y values, right? So all the y values stay the same, then my x values all become positive, or opposite in this case, right? Opposite of the negatives are the positives. What if I reflected down the x-axis? Okay, x stays the same. My y values all become opposite. Okay, pretty easy. And then if I want to rotate 180 degrees, I'm going to go 90 to here and 180 to here. My feet are going to be on my head. My head is going to be on my feet. See that? Pretty simple. Everything flipped upside down because everything was the opposite. Now let's rotate clockwise. This is more complicated. I want to focus on one point when I rotate clockwise. I'm going to focus on point C. When I rotate clockwise, one of the things I want to do is I want to get to the origin. When I get to the origin, from point C, because I'm rotating about the origin, I'm going to go down 1 over 2. So what's my slope here?
Negative half.
Negative 1/2. In order to have a perpendicular line or